Mr. B. Dhanasega is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expertise in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We have the theory of computation, the subject that is as far as this particular series of lectures are concerned. And in the previous episodes, we have seen the finite automata, and then we have studied the push down automata, and finally we have seen the linear bounded automata also. So, they were recognizing the languages like the regular languages, then context free languages, and then context sensitive that is languages, and they are available in the order of their their powerfulness. Like the regular language is going to be the most restricted one, and then we had the context free languages. So, they are more powerful than the regular languages, but still lacking power when you are comparing with context sensitive languages. And then we have seen the context sensitive language. In the meantime, we have seen the that is pumping lemma meant for that is proving that the certain languages are not coming under the closure, the regular, and the languages which are not coming under the context sensitive with the help of respective pumping lemmas. So, as far as this particular episode is concerned, we are having the new that is device or new recognizer, which is actually recognizing the class of language called either recursive or recursively enumerable languages. So, in all the earlier cases, like whether it is going to be a finite automaton or it is going to be a push down automaton or it is going to be a linear bounded automaton. So, they all were used just for recognizing the strings or some languages, but whereas in the case of Turing machine is concerned, we find that they are capable of doing even computations also. So, we should know that is what kind of computation that can be carried out by a Turing machine, and then what is going to be the actual structure or the model for a Turing machine, and how it is processing strings, and then how it is going to process the various computations, and what kind of what are the varieties of or different kinds of Turing machines available, and how they are all used. So, how they are equivalent in terms of the language recognition power. So, these are all the topics we have as far as the Turing machine area is concerned. And let us start with the simple definition for the Turing machine. So, it is going to be a simple mathematical model for of a computer, and it is having a sequential that is access store, we call it as the tape, and it is recognizing recursive as well as recursively enumerable set, that is going to be the language of Turing machine. And in terms of the computation is concerned, it is capable of doing partially recursive functions, and all these are possible with the help of the finite control, which is actually reading or writing the tape content. So, in the previous cases, we were having exclusive input and output devices, and as far as the Turing machine model is concerned, both the input as well as output are all staying or kept in the same device, that is called the storage tape. So, we will initially load the input into the that is the tape, and then when we are proceeding further, that is when we are doing the recognition or during the computation, we will read from the tape and we will write on the tape itself. So, there will be always a finite control that will be taking care of what should be done for a read operation and what should be done for write operation based on the Turing machine design. So, here we have that is the information, we have the information about what it does. So, it can change the state from the current state to the next state, or it can write a symbol onto the tape, or it can move its head towards left or towards right, but all at there is exactly one at a time. It can change the state from one state to the other state, and it can move towards the left or right one position at a time, or even it can replace a symbol and then it can move towards left or right still it is going to be 1 at a time. So, all these are possible with the help of your Turing machines finite control. So, now what is going to be the actual definition for the Turing machine? So, we will be having a Turing machine, that is a device very similar to the finite automaton and all. Here also we have the component called Q, that is telling you the finite set of states. It should be always a non-empty set of non-empty finite set of states. And then here we have two different there is alphabets. One is going to be the input alphabet and another one is going to be the tape alphabet. But we should understand that the input alphabet is always going to be a subset of the tape alphabet. It is because of the input itself is initially loaded into the tape. We do not have any exclusive device for holding only the input. So, as in the case of the push down automata or even in the case of finite automata, we do not have any exclusive device for loading the input. So, we will be holding or we will be storing the input itself into the tape. So, always this sigma is going to be a subset of that is this gamma. So, we call it as the tape alphabet, gamma is tape alphabet, and then we are having the transition function called del. So, how we are that is how the Turing machine behaves for some input. It is fully described in terms of the del function, and whose definition here it is following. We will be having that is a state and a symbol from the tape alphabet. You read the current, what is going to be current state and what is going to be the symbol from the, that is the tape, and based on these two, what is going to be the tape current symbol, current state, and what is going to be the tape symbol. Now, we will be having there is 3 outputs. So, what will be your resulting state? So, there may be chance for the changing the state. So, what is going to be the new state? That is going to be your Q, and so what we will be writing onto the tape content, where from we have read a symbol. So, if you are that is reading a symbol from the tape, let it be some x, that is from your tape alphabet. So, now the x not necessarily that is should be only kept as x, it can be replaced even by y also. Sometimes it can be even retained as x itself. So, what will be the change for that symbol, that is a tape symbol. So, that is what your gamma, and after reading or even after writing, we will not stay on the same cell. So, there is a need for showing progress on the recognition process or the computation process, and that will be done by moving towards the right or towards left. So, the direction is going to be the third output as far as any Turing machine transitions are concerned. So, 2 inputs we will be giving and it is producing 3 outputs, the new state, the replacement given for the symbol which is there in the tape, and what is the direction to move after writing the tape content or after writing the output onto the tape, whether it should be a left move or to be a right move. So, this is about your transition function, and Q naught is going to be the place where do we start, that is the starting state of a transition function, your Turing machine. And there is a special symbol here we are having, this first time we are introducing, which is not there in a push down automata or even the finite automata. So, when you are having an infinite tape, so the input is not necessarily be an infinite, that is input, it is going to be finite number of symbols. So, when you are loading infinite number of symbols onto your tape, which is going to be where the tape is going to be infinite on both directions. So, how do you represent the places or the cells where there is no input at all? So, we will be denoting that B is the symbol which is present on the rest of the cells. If a symbol is there or if an input is available in the tape, it will be marked by the symbols from the input alphabet or from the tape alphabet. But whereas in the case of symbol, the absence of symbols, we will be marking B as a symbol there in the that is tape. And as usual, we want to have some finite or that is accepting set of accepting states, which is always going to be a subset of Q, which will be telling you. So, when do we terminate the entire recognition process? So, that is what makes the that is trigger that the language has been or the string has been accepted. So, that is about the definition of any Turing machine. So, now we have to study that is how we are deriving the strings, that is how the strings are processed by the Turing machine. So, we will be calling them that is the various configurations. So, the Turing machine will be initially in a configuration, then after reading the input it will change its configuration, then after reading the next input it will once again change the configuration, and the process will be done as long as valid moves are there, and or until up to that is like we have reached the final state, final configuration. So, once the final configuration reached, then we can say that the Turing machine is going to halt with an acceptance, or sometimes when there is no valid move at all, it will still halt, but with no acceptance. Sometimes the Turing machine will never halt, it will keep reading something like that is moving towards right or left, keep doing something. So, in that case the Turing machine not necessarily going to be a halting one. So, to find that is how the progress is done, or how the Turing machine moves from one configuration to another configuration, we will be making use of the terminology called the instantaneous description. So, this is very close to the derivations which we have studied as far as the context free languages are concerned. So, where there will be a sentential form, and from the sentential form we will find a variable, and that variable will be replaced by its corresponding right hand side, and then we will get a new sentential form, and from the new sentential form once again we will find a variable, replace it with the right hand side, you go for the next sentential form, keep doing, and this process will be continued as long as we have more variables on the sentential form. And when we find that there is no sentential, no variable on the sentential form, then we will declare that a string has been arrived, and if it is a string that we want to verify or for which we are looking for a derivation, then we will say it is accepted, or else we will not accept it. But here we will use the similar kind of derivation, but the name is going to be instantaneous description, and all these will be derived only from the content available on the tape and with the help of the transition functions which are given as far as the given Turing machine is concerned. Here is a description for your ID. So, we will just read whatever is available on the tape. So, it is going to be x 1, x 2, x I plus I minus 1, then x I, then x I plus 1, and finally it is going to be. So, there are x n number of, there is n number of symbols available, they are marked as x 1 2, there is x n, and the q here is actually logically present there, it is telling you what is going to be the current state. So, the state is not present as far as our tape is concerned, it is the one with the finite control, but not with the tape. But here for just for understanding, we have introduced that q in between, that q x I plus I minus 1 and x I, telling that the current symbol which is going to be pointed by the finite control is x I. So, now let us see that is how this configuration or how this current instantaneous description changes with respect to the various transitions. We are taking one transition function, that is like del of q comma x I is giving you, there is two inputs, one is q, the current state, and another is going to be the current tape symbol. So, current state is going to be q and current tape symbol is going to be x I. The output is going to be p comma y comma l. The meaning is we are jumping to a new state called p, and the replacement given for x I is going to be y, and after replacing x I by y, you move 1% towards the left. So, that is the meaning of this particular transition. Start from q, see that current symbol available on the tape is x I, and then change the configuration by changing the state first of all from q to p, and replace that x I by y, and then move towards left after doing that. So, the direction can be, that is either left or right, but in some cases it can even be 4 directions or even more. But in the standard version of your Turing machine, only the left move or the right move are allowed. So, now for this particular transition, let us see that is how the current ID is going to change, or how the configuration will be changing to a new configuration. So, what it says is read x I, replace it by y. So, we are having that is y here in the place of x I. As far as the source configuration is concerned, or the initial that is ID is concerned, we have that is x I, and now we are having y here. So, we can't find x I anywhere available as far as this particular configuration is concerned. It is because of that x I is alone replaced by this y. So, that is the first thing. So, replacement has been done, and next is we are going towards left after the replacement. As per this particular transition function definition, we should move towards the left. So, it means the finite control should move 1% towards the left. Earlier it was in between x I minus 1 and y. Immediately after replacing that x I by y, now you move towards 1% towards the left. So, you will be having the finite control in the place in between your x I minus 2 and x I minus 1, and what is going to be new state from where we have to resume the process or resume the, that is recognition process. So, it is going to be the p. So, the configuration x1 to xi minus 1 q xi plus 1 to xn is now replaced by x1 to xi minus 2, then p is the new state from where we have to resume the process, and then xi minus 1, then followed by y, then followed by xi plus 1 etc. up to xn. And the situation is going to be quite different. Suppose if you are doing or processing with the first symbol or with the last symbol, in that cases, that is in the end cases, like when your current finite control is available on the beginning of the tape or on the end of the tape. So, what will happen there? So, if I is equal to 1, it means your finite control, that is your q is pointing x1. The same output, that is you are going for a new state p and replace x1 by y and move towards left. So, the new output is this x1 is no more there. So, it is replaced by y, and as per this particular output we must move one position towards left. So, how will you do that? It is from the current position you move one position towards left. Actually, the symbol which we have replaced is the leftmost symbol. So, on the left of that always you will be having a blank only, nothing else. So, from this x1 you move towards left, that is going to be a blank, and now your finite control is pointing a position whose right is going to have a blank rather than a valid symbol. So, p then b. So, it is actually existing as a next to x1, which is a blank symbol. Now, since the move is going to be a left move, we will say that the new output is going to be p, then it is b, and y, which is a result of replacing x1 by y, and rest of the contents are all going to be same. We shall have a break. After the break, we will continue the lecture. Welcome back. And the next one is, suppose if it is going to be n, like when I is going to be n. So, here the case situation is x1 to xn is or the symbols available in the tape, and now the finite control is available somewhere here, that is this is your q, this is a place where your q is available. So, what will happen, suppose if it is going to be the last symbol where you are that is the replacement is to be done. So, the output here is x1 to xn minus 1, there is no change, only that xn is replaced by y. So, xn has been replaced by y there, and now since the move is towards left, so the new finite control your p has to be available in between xn minus 2 and xn minus 1. So, the output is x1 to xn minus 2, then p, then xn minus 1, and then finally it is going to be y. So, these are the three cases which we are studying as far as the right, that is move is left is concerned, but the situation is going to be different when the move is going to be the right. Like for example, suppose if the transition function is del of q comma, that is xi is equal to p comma y comma r. So, now what will happen? So, the same thing, if it is going to be some xi, then replace it, instead of moving towards left we will be moving towards right, and when the symbol current symbol is going to be the leftmost symbol, what will